Hi, I'm Nathan Martin, and you're watching my ENME 435 final project video. Today I'm going to teach you how to build your very own LiDAR sensor, from construction to calibration to testing to gathering your data and finally turning it into a mesh to be 3D printed. I've chosen to scan these pipes outside of ESJ. The steam pipes at UMD are an icon, constantly walking through sulfur-smelling smoke. Here's the LiDAR sensor that we'll be building. The print file was made by a former student in ENME 435, but what it does is it keeps this Raspberry Pi camera and this line laser exactly 12 inches away from each other so that we can calibrate it properly. The laser is controlled by an Arduino, and the Arduino is powered by the Raspberry Pi on board. Both of these then can be powered through your computer by connecting the Raspberry Pi through a USB port into your computer. The LiDAR works using a parallel laser and camera. As the object that you're measuring moves further away from the device, its image will move closer to the center of the camera's field of view. We will calibrate our LiDAR system so that depending on the exact pixel location of the image, we can know exactly how far away our object is from the device. Because we are using a line laser, each measurement that we take will capture multiple horizontal points. There are two steps to calibrating your LiDAR system. The first is to make sure that the line laser is pointing perpendicular to the camera. This ensures that any objects at the same distance will be listed as being at the same distance. Second, you're going to want to take test measurements between 0 and 10 feet and plot them on a curve to figure out the exact constants of R0 and RPC for your specific setup. As you can see now, the line is directly vertical when compared to the reference green bars when I point the laser up at the ceiling. And here's my calibration setup. I have a white platform between 0 and 10 feet away, with a measuring tape set up alongside it and my laser sensor set up so that it is level and always in plane with the door. After you're all set up, you're going to position your setup between 0 and 10 feet and take a scan using the laser alignment code on Dr. Mitchell's GitHub. Once you've gotten all of your images, bring them into Python and run the laseralignment.py script. What this will give you is a plot where the points are your expected data points, and the line is calculated using these values of RO and RPC. Change RO and RPC until your plot and lines align, just like mine. Here's my LiDAR setup outside at the target for scanning. You can see the setup there with the Pi camera and the laser connected to my computer, which is SSH DIN for control. To scan your target, you're going to point the laser at the bottom of it and then slowly sweep it up to the top, taking an image every 2 to 3 degrees for processing. To take an image of your target, you're going to run the datacollection2.py script. After you run it, it will ask you for an angle, which you can get off of your phone that we're using as an IMU, an accelerometer. My first image is going to be at an angle of minus 30 degrees, so I input 330 degrees into my computer and press enter. We can see it right here, where I have the pipes and the line that I've taken, which will have my range measurement. This measurement is mostly flat because that area is mostly flat, but that is what I will continue to do every 2 degrees going up to the very top. A thing of note on this object are the different posters here and flyers, such as this one, which might make my scan an interesting shot, but also the light that's happening here. College Park, famous for its light pollution with all of this construction going on and lights flashing right here. So when I have to scan this side, it may be slightly more difficult. It's also important to note that I won't be able to scan the very top of those pipes, but I will be able to scan the base and all the way up to them. And then I can either fill that in the point cloud after or just have a part that is not quite completed. Because of the geometry of these pipes, I can't actually only take 4 scans, because if I'm standing on this direction, I won't be able to see the pipe behind. So I'm going to be taking 5 scans. The next one from this direction, and then one from this direction, instead of a single one from straight on. After taking 2 of my scans, tragedy struck. I saw my tripod just slowly teeter down and fall, and it landed directly on top of my mount. My original tripod mount snapped in half, and even, you can see here, this fell in half and I had to re-glue it back together. This ended up taking another day off of my time, but I got a new tripod and went back out to scan the very next evening. In order to process this data, once again, I used the row and RPC values that we calculated in homework 6, and then ran the datageneration.py script, which loaded in all of the JPEG files that I created and applied the mask, which turns our original image on the left to look like the image on the right, with the red lines the only white spots that we can then process. Here we can see that there's quite a bit more noise applied to these images. There was a lot more light out by the pipes that I scanned compared to being in my apartment, which meant that I had to edit the mask in order to get proper data to come out of this. After inputting all of these images, I then got the output here of these pipes. We can see that there are clearly 2 pipes going up there and the base at the bottom, which is flat. We can even note one of the posters, seen right here in the picture, that I called out in the image as a place where we might get some fun artifacts.
After turning each of those scans into a point cloud, it's time to head to MATLAB. To plot a point cloud, you want to use the function pointCloud to read in that text file into X, Y, and Z data. I then chose to rotate and translate my different point clouds around, and I'll show you the process of how I did that shortly. Here we can see that I've plotted 4 of my scans, and I've aligned all of those already, but I'm going to walk you through the process of aligning my 5th scan. So here are the 4 scans that I've already aligned. You can see that the 2 pipes are very clear here. On this 5th scan, the last pipe is still clear, but it's far away. To move it, the first thing that I do is 0 the new pipe. We can see the position in the y-axis, the position in the x-axis, and the position of the z-axis. So I'm going to move that up to 0 to match the other pipes. I do that right here using the rigid transform 3D function, which I can now run again. And now that that's loaded, we can see that the pipes are now overlapping each other. I'm then going to rotate this cyan pipe until we can see that the pipes are now facing in the same direction, but there's still some small offset that I need to correct for because this pipe is supposed to be over here. And there we can see the final point cloud collected. To combine all these point clouds, I used the PC merge function to combine. After saving that point cloud to a file, I'm opening it in a program called Cloud Compare, which is great at manipulating point clouds. So I'm going to open my points.py file and apply all of this, and here you can see my point cloud. I have quite a few points that are outside of where we actually want the image to be, so I'm going to erase all of those. The way that you do that is by selecting your point cloud on the top left, and then going to this scissor icon, and then you can draw shapes around the points that you'd like to get rid of. Once I press the right-click button, it finalizes it, and I can go here in the top right to remove those points. I've now finished segmenting the mesh, and so I'm going to press the checkmark button again and delete the remaining points. Now we can see my final finished point cloud that I can save to any point cloud format that I'd like, including .text or .py. Here we can see my point cloud. If I select the point cloud and then subsample it, selecting with a minimum space of 1 between the points, I can simplify the mesh down to remove some of the chaos within it. I'm then going to assign normals onto the points. You do that through Edit, Normals, Compute, where I'm going to once again use the default options. Now when the points are facing towards me, they'll be light, and when they're facing away from me, they'll be dark. I've noticed that this program's normal function is much more reliable than the one in MeshLab, so that when I mesh it, right here, using again the default options, I get a mesh that is a good approximation of the pipes that I'm expecting without all of the holes in the geometry. I do have, at points, a small floating section here, which I think is because of the scan that I took was a little bit unreliable on this side because I had dropped my LiDAR mount and broke it in half. But this scan is very reminiscent of the pipes that I'm trying to create. So I took this into Prusa Slicer, where I'm going to slice it for my Prusa Mini 3D printer, and I will be giving this model to Dr. Mitchell. Thank you for watching.